Hey, Math 30-1s. Today we are going to do our trig 3. We're going to do some identities. So what we're going to need today is we're going to need our formula sheet. Okay, just want to make sure my hat doesn't get in the way of that. All right, so make sure you have your formula sheet because you're going to be using this whole side down here, all these different identities. Okay, so first of all, let's figure out what an identity is and how it compares to an equation. So an equation is a mathematical equality that is true for only one very specific value, such as you can see in the question here, 2x minus 3 is equal to 9, right? That only is true when x is equal to 6, so that's an equation. It's only one value. I can solve for x here, and when I solve for x, I have the value that it's equal to. Okay? So I could solve for this x, and x ends up being 6. Sorry about the color here. It's kind of a weird color. Okay. Now, an identity is a little bit different. An identity is something that is true for all cases of x, not just the x's, like x equal to 6 or one very particular. So it's true for all cases. How they usually work is that you usually have x's on both sides. Sometimes you could just have a number on one side and just the math on the left-hand side just might end up always being that same number. So these kind of things they're a little bit tricky when I'm solving when I'm proving these identities. You can't really solve them because there's so many answers, an infinite number of these answers. So when I'm proving them, you can't cross over between the two sides. You can't move all the x's to one side and solve for x. Because if I do it, you're probably going to run into an error. You're going to run into a situation where you have like 1 is equal to 1, right? Or 2 is equal to 2, or x is equal to x, right? If you do that, then that just means, like we talked about that before in system of equations, that you have an infinite number of solutions. Okay, so we're looking at these 6 examples down here. We're just going to try to identify, are they considered identities or are they considered equations? Now, there's a lot of weird things about this. Like some of these you probably won't know unless I tell you right away that they're identities or equations. But the equations here are the ones where they have very particular answers, right? So like saying cos is equal to a half. Yeah, sure, there's an infinite number of answers, but not all x values would make this equal to true or make it equal to a half, right? So if I put cos 15, you're not going to get a half. If I put cos 90, you're not going to get a half. But if you put cos 60, I do. Right, that's good. So cos 60 will be an answer, but it's not true for all x values, right? It's got to be true for all x values to be an identity. Okay. There's a few other ones in here like cosecant. Cosecant there, that's an equation. This sine squared one is equal to 1. That's an equation as well. And really quick way to just identify, is it an equation or is it a identity, is you graph it. You graph the left-hand side, you graph the right-hand side. Are they essentially the same thing? Right. So let me show you on some of these on Desmos, and you can see that you can identify identities pretty quickly using those. Okay, so see here, I put a bunch of these examples into my Desmos here. So we have secant squared and 1 minus tan squared. So that's either side of the equation. So I turn it on. You can see secant squared. It's this kind of weird repeating parabola-esque kind of things. Not really parabolas. They're more hyperbolic in nature. And then if I put on the other one, you can see that it's right on top of it. So they mentioned they are the exact same thing. So if I think I could change this to be a bit thicker, you'll see it change a bit better. Okay, yeah, so you can see that those two are exactly the same, right? So that at least verifies that they're identities. It doesn't prove that they're identities, but it gives you a good indication that, yeah, these ones could be identities. Now I can probably go around to try to prove that they could be identities later on. We'll talk about proving them later. Another one here would be like sine squared plus cos squared. You're thinking, okay, that doesn't seem like it could be identity because you go down, remember the one we did before, sine squared plus sine is equal to 1. This sine squared plus sine, that's equal to that. And then there's 1. Okay, they're not the same. They have solutions. You can see there's a bunch of solutions here. But they're not infinite number solutions. They're not exactly the same for all x values. So this x value up here is different than this x value that's down here. Okay? So those are not identities. So this kind of looks like the same idea, sine squared plus cos squared. Okay, so I'll put that line there, but then as soon as I turn this one on, you notice that they're exactly the same. Okay, so we'll talk about why that one's true, why that one's an identity. This one's a more, this is one we see in these reciprocal ones. Remember, cosine and secant are both reciprocals of each other. So if I take the reciprocal of secant, I should just get back cos. And yeah, you can see that they're the same. Okay. Now there are restrictions to these. You can't have certain x values or certain y values because you might divide by 0, but that's fine. Right? As long as the graphs look somewhat the same, you don't have to worry about too much about the restrictions. We can call them identities. Okay. So these ones here, the identities, these ones here are the identities. So when you graph the left-hand side and the right-hand side, they're the same. You can verify them by putting in values of x too, but you just might luck out and find an equation solution rather than finding if it's an identity or not. So a few identities that we know already that are on our formula sheet that we've played with before are, here we got the reciprocal identities, like cosecant is equal to 1 over sine, secant is 1 over cos, et cetera, et cetera. Then we got the tangent and cotangent identities. Remember when we're dealing with sine and cos, if we're on the unit circle, I can say, as long as we're on the unit circle, I can say sine is equal to y and cos is equal to x, right? So as long as we're on the unit circle, I could say these two things. Right? So we get sine over cos. Sine over cos is going to be y over x, which is going to be the opposite over adjacent, and this is going to be x over y. Okay. Now the identities down here these don't matter if it's on a unit circle because they're going to both have hypotenuses on them, and when I divide a hypotenuse by hypotenuse, it cancels out. Okay. But for the unit circle one up here, as long as we're on the unit circle, I could say sine is equal to y, cos equal to x. Okay, so there are a few identities here that we haven't seen yet. These ones are called Pythagorean identities. Now the Pythagorean identity is pretty simple. As long as we're on the unit circle, right? Remember, if we're on the unit circle, I can say sine is y and cos is x. Okay, so if I were to draw that out, okay, here's my angle theta. This is my y, this is my x. And if I use Pythagorean theorem, if I'm on the unit circle, then x squared plus y squared should equal 1 squared. There you go, right? Now, if I go back up to the top there, I can say, oh, cos is x. So this is technically cos squared. And sine is y, so this is sine squared theta. It is equal to 1. So that's where this first identity comes from. The other identities are just rearranging it. Oh, now let's minus over the cos x or cos squared. Let's minus over the sine squared. So these just all come from rearranging each other. Okay, now to show that this works not on the unit circle, because we use the assumption that we're on the unit circle here, we can go with the other way saying, okay, what is cos or x squared plus y squared? If I'm not on the unit circle, it doesn't have to equal 1, it could equal r squared. Now, if I divide both sides by r squared divided by r squared is 1. So you get the 1 on this side. Then x over r, that would be the adjacent over the hypotenuse. Well, that's going to be cos. That'd be cos when you're not on the unit circle. And then on the other one over here, y over r squared is equal to 1. So again, here we got cos theta squared. Sorry, I put the square on that side. We'll just get rid of that 2 there. Okay. And then I got sine squared theta. So 1 as well. Okay. So yeah, so this holds true even if you're not on the unit circle. Right? If you're on the unit circle, it's pretty easy to see that it works. But if you're not in the unit circle, you can make it equal to r squared, divide the r squared over, and eventually it just works itself out. So it is an identity, so it's a true identity. And now we can use that identity to help us show other identities. So this is me proving this identity. So I proved it by using some knowledge about Pythagorean theorem. And now I can use this identity to solve for other identities, such as these next ones here, right? These ones are just rearranging versions. But where does a tan squared plus 1 is equal to secant squared come from? Okay, so we're going to use the identities that we have above here, right? So the reciprocal identity, the quotient identity, the Pythagorean identity, we're going to put them together to prove these other identities, or at least make these identities. Okay, so we're going to start off, I'll start off here with cosine. I'll start off with this identity, cosine squared plus sine squared is equal to 1. And what I'm going to do with this is I'm going to divide both sides. I'm going to say, I'm just going to take both sides here. I'm going to divide them both by cos squared. Okay, everything by cos squared. Cos squared divided by cos squared is 1. Okay, looking promising. Sine divided by cos. If I look up here, sine divided by cos is tan. This one's being squared, so this is going to be tan squared. Okay, and then 1 over cos squared. So 1 over cos is secant. Go up to here and say, oh, that's equal to secant. So I can replace this with a secant squared. So that's where this identity comes from. Okay, so it's just the Pythagorean identity. We just slightly modified it by dividing both sides by cos theta squared, and we get this new identity. Okay, we can use that one to prove other ones. And you look at the one below it, all that one is just the rearranging. Just the one is being minused over. So both of these are from the same thing. Now the other one there starts off the same way. But rather than dividing by cos, I just divide by sine. You can quickly see that that is going to end up being cos over sine. Cos over sine, if you look up here, is cotangent. Oops, cotangent squared. Sine divided by sine is going to be 1. And then 1 over sine is going to be cosecant. And that's being squared. There you go. So that one shows that identity, and that's just the rearranging of it. Okay. So that's making new identities. There's also showing that you can prove them as well by using those identities. So I can reverse this. I can say, okay, here's my 1 plus cotangent squared. Now prove that this actually works. Okay. So I'll show you that process later on. How do I reverse this to prove it? As long as I get down to just really simplified left side is equal to right side, it should work out nicely for us. And you'll see. There you go. Okay, so for these examples here, which I'm going to do is going to in the next video, we're just going to simplify these. We're going to use these identities that we have up here, the Pythagorean identities, the reciprocals, and the quotients. We're going to simplify these down to a single trigonometric value, or a single expression. So this is kind of the introduction to how we prove these. We simplify it down as much as we can, and then we simplify the other side of the equation, if there was another side, down as much as you can to see, do they equal each other? That's the whole goal of identities, is does the left-hand side actually equal the right-hand side? To prove it, we just kind of simplify it down to make it look the same. If they look the same, then we can prove that way. So I'll see you in the next video.